video, we're going to work with the derivatives of the inverse trig functions. There's two different notations that we can use when we're talking about inverse trig functions. Some textbooks use a -1 to denote an inverse, and so y equals sine inverse of x is one notation, and another notation is to say it's the arc sine of x. And when we do these, the angles have to be restricted in order for the inverses to be functions. And so for sine, the range or the angles that we can get from doing sine inverse are restricted to -π/2 up to π/2. So if we're going to derive what the derivative of sine inverse of x is, we can rewrite y equals sine inverse of x as the equivalent statement x is the sine of y. And y is some function of x, and its derivative will just denote as dy dx. If I take the derivative of both sides of this equation, x equals sine of y, then the derivative of x is 1. The derivative of sine is cosine, so we'll get a cosine of y. But this is a chain rule problem because y is some function of x, so I have to multiply this by the derivative of y, which we're just calling dy dx. If I solve that for the derivative, or dy dx, we get dy dx is 1 over cosine of y. But we want the derivative to be in terms of x, so we're going to use some identities to rewrite this. So we know that sine squared of y plus cosine squared of y equals 1. That's the Pythagorean identity. We also know the equation we started with is that x equals sine of y. So I can rewrite this as x squared plus cosine squared of y equals 1. And if I solve for cosine squared, I get cosine squared of y equals 1 minus x squared. And then if I take the square root of both sides, I get cosine of y equals plus or minus the square root of 1 minus x squared. However, we are limiting cosine of y to the angles of -π/2 to π/2. And in those two quadrants on the unit circle, cosine is positive. So we're not going to use the negative here. We're just going to say cosine of y is the positive square root of 1 minus x squared. So my dy dx, my derivative, is 1 over the square root of 1 minus x squared. And there is a domain restriction on that. We're going to need x to be in between -1 and 1. So what we have here is that the derivative of sine inverse of u is equal to 1 over the square root of 1 minus u squared times u prime. And the reason I've written it that way is these derivatives are going to be more involved than just writing down what the derivative of the inverse trig functions is. They're going to be chain rule problems. So if there is something in the argument to the inverse sine that is more complicated than just an x, we'll have to multiply the result by the derivative of what is in that argument. Using the arc sine notation, the derivatives of the 6 trig functions are listed here, And they are in the notes that you can print out as well, listed for you. So here's the first four: arc sine, arc cosine, arc tangent, arc cotangent. And what you'll notice is with all of the co-functions, we're going to get a negative of what the other function is. And there's arc secant and arc cosecant. So let's work some examples. We want to find the derivative of arc sine of 2x. So in this problem, my u is 2x and my u prime is 2. So when I plug in to the formula for the derivative of arc sine, I get 1 over the square root of 1 minus u squared, but u is 2x, times u prime. And if I clean this up, I'll have 2 over the square root of 1 minus 4x squared, because when I square 2x, I square both the 2 and the x and get 4x squared. Y equals arc cosine of x over 4. In this case, my u is x over 4, and my u prime then is 1/4. So if we plug this into the formula for arc cosine, we will get -1 over the square root of 1 minus u squared, where u is x over 4, times u prime, which is 1/4. And if I rewrite that, I'll get -1 over 4 times the square root of 1 minus x squared over 16. Now we have a compound fraction. We're not supposed to do that in math. That's a fraction inside of a fraction. So we want to try to get rid of this 16 here. And I see that I can do that if I move the 4 inside of my radical and multiply everything by that 4 squared. Right? Outside the radical I have 4, but if I put it under the square root symbol, the square root of 16 would be 4. So what we're going to do is rewrite this as 16 times 1 minus x squared over 16. And when I distribute that 16, I get -1 over the square root of 16 minus x squared. Okay, we have y equals arctan of 3x. So for this one, my u is 3x. My u prime is 3. The derivative is 1 over 1 plus x, or u squared, and our u is 3x, times u prime. And I get 3 over 1 plus 9x squared. Okay, I have y equals arc sine of the square root of x. So my u is the square root of x, which I can also write as x to the 1/2. So my u prime is 1/2 x to the -1/2, or 1 over 2 times the square root of x. So my derivative is 1 over the square root of 1 minus u squared, where my u is the square root of x. So we're going to square a square root here, times 1 over 2 times the square root of x, which is our u prime. And I get 1 over 2 times the square root of x times the square root of 1 minus x. Now that's not very nice to look at, but when we have a square root times another square root, we can put them together under the same radical sign. So that's what I'm going to do here. I'm going to rewrite this as 1 over 2 times the square root of x times 1 minus x, and I'll distribute that x, and I end up with 1 over 2 times the square root of x minus x squared. Okay, we have an arcsecant of e to the 2x here, so my u is e to the 2x, and then my u prime, well, this is another chain rule problem. The derivative of e to the something is e to that something, but then we have to do times the derivative of the inner function, so this is going to end up being 2 e to the 2x. Using my formula for arcsecant, I'll get 1 over the absolute value of u times the square root of u squared minus 1 times u prime. Now, when I look at this, the absolute value of e to the 2x, e to the 2x is always a positive number, so I don't really need the absolute values there. But I also see that I can simplify e to the 2x divided by e to the 2x here. And I will get 2 over the square root. If I square e to the 2x, that's a power of a power, which means multiply exponents, so I'm going to get e to the 4x minus 1. Okay, y equals arc cotangent of 6x, so I'm going to have a u of 6x here, and my u prime is 6. Then the formula for arc cotangent is a negative 1 over 1 plus u squared, where our u is 6x, times u prime, and I get negative 6 over 1 plus, if I distribute that power, it's going to be 36x squared. Okay, now we're going to do some examples using the other notation for the sine inverse of u. And in this problem, we have u equals x squared minus 1. Then u prime will be 2x. So my derivative is going to be equal to 1 over the square root of 1 minus u squared times u prime. And if I just clean that up a little bit, I get 2x over 1 minus x squared minus 1 squared. And I could multiply that x squared minus 1 squared out, but there's really no reason to do so. Okay, the derivative of cosine of sine inverse of x. So this is a chain rule problem where our inner function is sine inverse of x, and its derivative is just the formula. So when we take the derivative of this, the derivative of cosine is negative sine of sine inverse of x times the derivative of sine inverse of x and sine inverse are inverse functions, and when you do a composition of inverse functions, the result is you just get the argument to them. So we're going to get negative x over the square root of 1 minus x squared for this problem. Okay, in this problem, we have a product rule. So I see my first function is x, and my second function is sine inverse of x. So our derivative is going to be the derivative of the first, derivative of x is 1, times the second function, plus the first function times the derivative of the second function, which I just get that from the formula for the derivative of inverse sine. And if we just clean it up a little bit, I don't need that 1. And that is my answer. Okay, we've got another chain rule going on here where my u is natural log of x and my u prime is 1 over x. So the derivative here is going to be 1 over the square root of 1 minus u squared, where our u is the natural log of x, times u prime. And there's not a whole lot I can do to simplify this, but I can rewrite it, just make it look a little bit nicer by writing it as x times the square root of 1 minus natural log of x squared. Okay, on this problem, we have a chain rule inside of a chain rule. Our u for the argument to sine inverse is e to the sine x. Its derivative then, when we take the derivative of e to the something, we get back e to the something times the derivative of that something. The derivative of sine is cosine x. So then, if I use the formula for the derivative of inverse sine, I get 1 over the square root of 1 minus u squared times u prime, which is e to the sine x, times cosine x. And if we clean that up a little bit, I'll write my numerator is e to the sine x times cosine x, and in my denominator, I am going to square the e to the sine x term, and that's power of a power means multiply exponents, so I can write this as e to the 2 times sine x. Okay, the derivative of inverse cosecant, where our u is the square root of x. Well, we did one with arc sine earlier, so I know that my u prime here is 1 over 2 times the square root of x. And using the formula for cosecant, I get negative 1 over the absolute value of u times the square root of u squared minus 1 times u prime. Now, the square root of x is a positive number, so I don't really need the absolute values there. And when we do the square root of x times the square root of x, we're just going to get x. So this becomes negative 1 over 2x times the square root. When I square the square root of x, I just get x minus 1.